Welcome to Part 2 of the Android Interview Series 2024, curated by Anatom Murthy and published in Pro Android Dev. This segment is tailored for intermediate Android developers aiming to deepen their expertise. We'll explore Android architecture components, build processes, unit testing, and debugging tools. Whether you're preparing for interviews or seeking to strengthen your development skills, this series offers practical insights and real-world examples. Let's set the stage for a journey through advanced Android concepts, building on the basics covered in Part 1 and paving the way for future topics like Java, Kotlin, and Jetpack Compose. Android architecture components are a set of libraries introduced by Google to help developers build robust, testable, and maintainable applications. These libraries address common challenges such as managing UI lifecycle changes and handling data persistence efficiently. By leveraging these components, developers can reduce boilerplate code, improve modularity, and ensure data consistency across configuration changes. The architecture encourages the use of MVVM, separating UI and data logic for cleaner codebases. Understanding these components is essential for tackling app complexity and creating scalable Android solutions. Android architecture components help manage app complexity through lifecycle awareness, data consistency, and testability. Lifecycle-aware components prevent memory leaks and crashes by automatically managing data updates in sync with activity or fragment lifecycles. ViewModel and LiveData ensure data remains consistent across configuration changes, eliminating manual handling. The modular structure makes unit testing easier, while Room and other components reduce boilerplate code. By encouraging MVVM architecture, these components maintain a clean separation between UI and data logic, simplifying maintenance and scaling. Primary Android architecture components include ViewModel, LiveData, Room, Repository, Navigation Component, and WorkManager. ViewModel stores and manages UI-related data in a lifecycle-conscious way, allowing data to survive configuration changes. LiveData is an observable, lifecycle-aware data holder, ensuring UI updates only occur when components are active. Room provides an abstraction layer over SQLite, simplifying database management. Repository acts as a single source of truth for data, while Navigation Component manages complex app navigation. WorkManager handles reliable background task scheduling, ensuring tasks like data syncing are executed. LifecycleOwner is an interface representing an entity with an Android lifecycle, such as an activity or fragment. It allows components like LiveData and ViewModel to observe lifecycle changes and manage resources efficiently. By observing only when the LifecycleOwner is active, memory leaks are prevented and updates are paused or detached when the component is stopped or destroyed. This ensures a consistent user experience, as data is not lost during events like screen rotation. Lifecycle-aware programming is key to robust Android development. Using lifecycle-aware components in Android development is crucial for preventing memory leaks and ensuring efficient resource management. Observers are automatically removed when the lifecycle is inactive, reducing manual cleanup. UI updates occur only when components are active, and components can respond accurately to lifecycle changes. This leads to a more consistent user experience, especially during configuration changes like screen rotations, where data persistence is essential. The ViewModel class is designed to store and manage UI-related data in a lifecycle-conscious way. Its main purpose is to retain data relevant to the UI through configuration changes, such as screen rotations, avoiding unnecessary reloads. ViewModel keeps UI controllers lean, focusing on UI tasks while business logic and data handling are managed separately. It is lifecycle-aware, releasing resources when the UI component is destroyed, and can be tested independently of UI elements, making it ideal for unit testing. ViewModel survives configuration changes like screen rotations, keeping UI data intact even when activities or fragments are recreated. This reduces the need to reload data and keeps UI controllers focused on presentation logic. ViewModel is lifecycle-aware, releasing resources when the UI is permanently destroyed. Since ViewModel does not reference UI elements directly, it can be tested independently, improving code organization and maintainability. Save state handle is a key-value map available in ViewModel for storing data that should survive process death. While ViewModel retains data across configuration changes, it loses state if the app process is killed. Save state handle leverages Android's save state feature, allowing critical UI state to be preserved and restored automatically. This is especially useful for retaining user input, scroll positions, or other data expected to persist across app restarts. LiveData is an observable, lifecycle-aware data holder class that respects the lifecycle of Android components like activity or fragment. By observing LiveData, UI components automatically receive updates when data changes, enabling a reactive architecture. LiveData works seamlessly with ViewModel, ensuring UI state is retained and updated without manual intervention. It's ideal for managing asynchronous data sources, such as network or database data, and decouples UI from data sources for cleaner code. LiveData is an immutable data holder, providing a safe, read-only view of data for UI components. Mutable LiveData, a subclass of LiveData, allows data modification through setter methods. Mutable LiveData is typically used inside ViewModel to manage and update data in response to events, while LiveData is exposed to UI components for observation. This separation ensures data integrity and prevents unintended modifications from the UI. Transformations in LiveData, such as map and switch map, allow developers to manipulate or transform data held in one LiveData into another. The map function applies a transformation to each value, while switch map is useful when the transformation depends on another LiveData source. These utilities enable reactive data flows and simplify complex UI updates, making it easier to manage derived or dependent data. Mediator LiveData is a subclass of LiveData that can observe multiple LiveData sources simultaneously. It acts as a mediator, combining data from various sources or reacting to changes in one or more LiveData objects. This is useful for scenarios where you need to produce a unified result from multiple data streams, such as combining user profile and settings data for a single UI update. Single Live Event is a custom LiveData subclass designed to handle events that should only be triggered once, such as navigation or displaying a toast. Unlike regular LiveData, which may re-emit values after configuration changes, Single Live Event ensures the event is observed only once, preventing multiple triggers. This is essential for one-time actions in the UI, maintaining predictable behavior during lifecycle changes. Room Database is part of Android architecture components, providing an abstraction layer over SQLite for robust and easy database interactions. Room verifies SQL queries at compile time, reducing runtime errors. It uses annotations to minimize boilerplate code and works seamlessly with LiveData and ViewModel for lifecycle-aware data management. Room supports database versioning and migrations, making it ideal for scalable and maintainable apps. Room handles database migrations by allowing developers to define transformation strategies for schema changes. When the database version is incremented, migration objects specify how to update the schema, such as adding new columns or modifying tables. This ensures data consistency and prevents errors during upgrades. Room's migration support makes it easier to evolve your database structure as your app grows. Room supports relationships between entities using embedded classes and the @relation annotation. For example, a one-to-many relationship can be modeled with a user entity and multiple address entries. The @relation annotation defines how entities are connected, enabling Room to fetch related data efficiently. This approach simplifies complex data models and ensures accurate data retrieval. ViewBinding generates binding classes for each XML layout, allowing direct access to views without fine view by it. It's simple and lightweight, ideal for straightforward UI access. Data binding, on the other hand, enables binding data directly to XML layouts, supporting two-way binding and reactive UI updates. Data binding is powerful for complex applications, especially those using MVVM, as it simplifies UI updates and supports binding expression. Data binding errors during compile time often arise from incorrect expressions, type mismatches, or improperly defined variables in XML layouts. To handle these errors proactively, enable ViewModel validation and use bindable annotations for properties requiring two-way binding. Custom binding logic can be implemented with @binding adapter methods, reducing XML syntax errors and keeping code clean. The navigation component provides a cohesive framework for defining navigation paths, handling fragment transactions, and managing backstacks. Developers can define all app navigation in a single navigation graph XML file, visualizing the app's flow. The component simplifies fragment transactions, automatically managing backstack and lifecycle complexities. Using NavController, navigation between fragments becomes straightforward and less error-prone. SafeArgs is part of the navigation component, enabling safe and type-checked data passing between destinations in a navigation graph. It generates argument classes, ensuring compile-time checks and reducing runtime errors. Implicit intents, in contrast, request actions from other apps or components without specifying the exact handler. SafeArgs is ideal for predictable navigation, while implicit intents are used for broader actions like opening URLs or sharing content. Deep linking with the navigation component allows your app to open specific destinations directly via URL or URI. By defining deep links in the navigation graph, you enable navigation to particular fragments or activities from external sources like notifications or web links. The navigation component handles navigation and populates arguments automatically, streamlining user access to targeted screens. Best practices for the navigation component include using a single main activity with multiple fragments, leveraging safe args for type-safe data passing, and keeping the navigation graph organized. Configure up and back navigation to respect the back stack, define deep links for external access, and set up custom animations for smooth transitions. Use pop-up to attributes to manage the back stack and optimize memory usage. The paging library simplifies loading large data sets by displaying data in chunks or pages, optimizing memory usage and performance. This approach is especially useful for lists fetching data from local databases or remote sources, ensuring smooth scrolling and efficient resource use. Paging enables scalable data handling, making it ideal for apps with extensive lists or feeds. Paging source defines how to load data pages from a source. Paging data holds paginated data for UI rendering, and paging adapter submits paging data to the UI, handling diffing and display. Together, these components enable efficient, scalable list management, allowing apps to load and display data incrementally without overwhelming memory resources. The paging library uses load state to track data loading states, loading, error, and not loading. Observing these states allows the UI to react appropriately, such as showing a loading spinner or error message. This ensures a responsive user experience, even when dealing with large or remote data sets. Refreshing data in the paging library is straightforward. By calling adapter refresh on the paging adapter, you reload data from the start, ensuring the UI displays the latest information. This mechanism is useful for implementing pull-to-refresh features or updating lists after data changes. Remote Mediator fetches data from remote sources, such as APIs, and stores it in a local database. This enables offline access to previously loaded pages and manages boundary conditions for loading additional data. Remote Mediator keeps local cache synchronized with remote data, handling loading states and errors for a seamless user experience. WorkManager is an Android library for handling background tasks that need guaranteed execution, even if the app is closed or the device restarts. It supports constraints like network connectivity and battery level, retries tasks on failure, and allows chaining multiple tasks with dependencies. WorkManager is ideal for persistent, deferrable background operations. WorkManager is used for guaranteed background tasks. Job Scheduler schedules jobs under certain conditions, and Alarm Manager triggers actions at exact times. WorkManager is best for tasks that must run eventually, Job Scheduler for tasks that can wait for device conditions, and Alarm Manager for time-sensitive operations. Choosing the right tool depends on task requirements and timing needs. WorkManager supports one-time work request for single tasks, periodic work request for recurring tasks, and unique work request to avoid duplication. These options allow developers to schedule background work flexibly, ensuring tasks run as needed without overlap or unnecessary repetition. WorkManager enables chaining multiple work requests using work continuation. This ensures tasks run sequentially or based on dependencies. For example, you can download, process, and upload data in a defined order, improving workflow management and reliability. WorkManager has limitations, such as a minimum interval of 15 minutes for periodic work and no guarantee of exact timing. Device constraints may postpone tasks until conditions are favorable. Alternatives include Job Scheduler for less frequent tasks and Alarm Manager for exact timing requirements. Understanding these constraints helps in choosing the right background task solution. Dependency injection, DI, is a design pattern that provides objects with their dependencies from external sources. In Android, DI simplifies dependency management, improves code readability, and makes testing easier by allowing mock dependencies. Popular frameworks like Dagger and Hilt automate DI, reducing boilerplate and managing dependency lifecycles efficiently. DataStore is a modern data storage solution in Android, replacing shared preferences for asynchronous operations. Preferences DataStore stores key-value pairs, while Proto DataStore uses protocol buffers for structured data. DataStore operates asynchronously, supports Kotlin coroutines, and guarantees data consistency across threads, making it ideal for scalable apps. To avoid memory issues with large datasets, use the paging library to load data in chunks and display only subsets at a time. RecyclerView efficiently recycles views, reducing memory usage compared to ListView. These strategies ensure smooth performance and scalability for apps handling extensive data. Android offers several ways to handle asynchronous tasks, including coroutines for sequential and readable code, WorkManager for guaranteed execution, and RxJava for functional reactive programming. A sync task is deprecated, so modern apps should use coroutines or WorkManager for background operations, ensuring responsive UI and efficient resource use. Memory leaks occur when objects remain in memory unnecessarily. Prevent leaks by avoiding long-lived context references, using weak reference for large objects, leveraging lifecycle-aware components like ViewModel and LiveData, and using tools like Leak Canary for real-time detection. These practices ensure efficient memory management and stable apps. Handle large image files efficiently by compressing and resizing images, using libraries like Glide, Picasso, or Coil for caching and loading, and opting for vector images or modern formats like WebP. Caching frequently used images reduces memory consumption and speeds up loading, ensuring smooth UI performance. ANR, application not responding, errors occur when the main thread is blocked for over 5 seconds. Prevent ANRs by running tasks on background threads, using handlers for communication, optimizing heavy calculations, and avoiding blocking operations in UI lifecycle callbacks. Responsive UI and efficient task management are key to avoiding ANRs. The Android build process converts source code, resources, and configuration files into an APK. Main stages include compiling code, processing resources, linking compiled elements, and packaging the APK. Gradle orchestrates these steps, ensuring efficient builds and customizable configurations for different app variants. Build variants combine build types like debug or release, and product flavors like free or paid, allowing customization for different requirements. Product flavors define versions of the app with unique features or configurations. This flexibility enables developers to target multiple markets or user segments from a single codebase. Gradle is a powerful build automation tool used in Android development to manage dependencies, compile code, run tests, and package applications. Its flexibility allows custom build configurations, task automation, and efficient incremental builds. Gradle is the foundation of the Android build system, streamlining complex processes. Gradle tasks are units of work performed during the build process, such as compiling code or packaging APKs. Developers can customize the build by adding custom tasks, modifying existing ones, or automating repetitive actions. This flexibility enables efficient project management and tailored build workflows. Gradle supports implementation, API, and compile-only dependencies. Implementation is internal to the module, API exposes dependencies to consumers, and compile-only is available only at compile time. Choosing the right dependency type ensures proper encapsulation and efficient build management. ProGuard and R8 are tools for code shrinking and obfuscation in Android. ProGuard removes unused code and renames classes, while R8 is faster and more efficient, combining shrinking and optimization. Both tools reduce APK size and protect code, configurable via build. Gradle. R8 is enabled by default in modern projects. Build types define configurations for development and production. The default types are debug, used for testing with debug symbols, and release, optimized for production with code shrinking and obfuscation. Custom build types can be defined for specific project needs, ensuring flexibility in app deployment. The Android Asset Packaging Tool, AAPT, compiles and packages app resources into an APK. It processes XML files, images, and assets, generating a binary representation and the RJava file for resource access. AAPT ensures resource uniqueness and merges resources from libraries, streamlining APK creation. Build speed can be improved by enabling Gradle daemon, parallel builds, incremental compilation, and build caches. Optimizing resource processing, such as reducing image sizes and using vector graphics, also helps. These strategies ensure faster builds, especially in large projects, enhancing developer productivity. Multidex allows Android apps to have multiple dex files, necessary when method references exceed the 65,536 limit. The Multidex support library manages multiple dex files seamlessly. Enable Multidex in Build, Gradle, and add the support library to handle large codebases efficiently. Versioning is managed with version code and version name in Build, Gradle. Version code is an integer for tracking releases, incremented with each update. Version name is a user-friendly string for display. Proper versioning ensures smooth updates and compatibility across app releases. Build config is a generated class containing build-specific constants, accessible in code. Manifest placeholders allow value replacement in Android Manifest. XML at build time, useful for customizing application IDs, API keys, or configurations based on build types or flavors. These features enhance build flexibility and customization. Signed APKs and app bundles are generated using Android Studio or Gradle command line. Provide a keystore file and signing credentials in build. Gradle. Signed APKs are used for distribution, while AABs enable optimized delivery through Google Play, ensuring secure and efficient app releases. APK is the traditional package format for Android apps, containing all resources and code in a single file. AAB, Android App Bundle, is a more efficient format, allowing Google Play to optimize delivery for each device configuration. AAB reduces app size and supports dynamic delivery, improving user experience. Reduce APK size by enabling ProGuard R8 for code shrinking, optimizing images, removing unused resources, modularizing the app, and using AAB for optimized delivery. These strategies ensure smaller downloads and faster installations, enhancing user satisfaction and app performance. The Android Profiler in Android Studio monitors app performance in real time, providing insights into CPU usage, memory allocation, network activity, and battery consumption. Its main components include CPU Profiler, Memory Profiler, Network Profiler, and Energy Profiler, helping developers optimize app behavior and resource usage. Use the Memory Profiler to identify memory leaks by monitoring allocations, taking heap dumps, and analyzing retained objects. Look for objects that should have been cleared but remain in memory. Tools like Leak Canary provide real-time detection and detailed reports, streamlining leak debugging. The CPU Profiler analyzes app performance, highlighting methods consuming the most resources. Record CPU activity, profile specific processes, and drill down into method calls to identify bottlenecks. Optimizing heavy processing tasks improves app responsiveness and user experience. Strict Mode is a debugging tool that catches performance issues and improper framework usage, such as disk writes or network operations on the main thread. Enable strict mode during development to enforce best practices and alert developers to problematic patterns, promoting cleaner and more efficient code. The Network Profiler monitors network activity, displaying metrics like request size, response size, latency, and status. It helps identify large payloads, slow endpoints, and HTTP errors, enabling developers to optimize data usage and resolve API issues for better app performance. Identify and resolve ANR issues by monitoring thread activity with the CPU Profiler, analyzing stack traces, and implementing asynchronous processing. Profiling heavy operations and providing responsive UI feedback, such as loading indicators, help mitigate ANRs and improve user experience. Debug release build crashes by implementing proper logging, using crash reporting tools like Firebase Crashlytics, and generating mapping files for deobfuscation. Test release builds on various devices and configurations to reproduce issues and ensure robust error handling in production. Android Debug Bridge (ADB) is a command line tool for communication between a computer and Android devices. It retrieves logs, runs tests, pushes and pulls files, and monitors app performance. ADB streamlines debugging, making it easier to troubleshoot crashes and optimize app behavior. Track memory usage with the Memory Profiler. Ensure proper cleanup of resources during activity lifecycle events, and analyze heap dumps for retained objects. Libraries like Leak Canary automate leak detection, helping developers identify and fix leaks related to activity and Fragment lifecycles. Layout Inspector provides real-time analysis of UI hierarchy, helping spot overlapping views or incorrect layouts. Constraint Layout Editor offers visual feedback on layout constraints, optimizing UI for different screen sizes. UI Automator Viewer inspects layouts of third-party apps, supporting comprehensive UI testing. Unit testing validates individual components or functions in isolation, ensuring each part performs as expected. In Android, unit tests focus on methods and classes without external dependencies. Reliable unit tests improve code quality, catch bugs early, and support continuous integration workflows. Good unit tests are isolated, repeatable, descriptive, fast, and independent. Isolation ensures tests focus on a single unit of work. Repeatability guarantees consistent results. Descriptive names clarify intent, speed encourages frequent running, and independence allows easy debugging. These principles ensure effective and maintainable tests. Unit testing focuses on individual components. Integration testing examines interactions between modules, and end-to-end testing simulates user workflows. Each type serves a distinct purpose, ensuring reliability at different levels of the application and supporting comprehensive quality assurance. Common frameworks for unit testing in Android include JUnit for test structure, Mockito for mocking dependencies, Roboltrick for JVM-based Android tests, and Espresso for UI testing. These frameworks integrate with Gradle, streamlining the testing process and supporting reliable test automation. Mockito is a popular framework for creating mock objects, allowing developers to simulate complex dependencies and focus on class logic. By isolating tests from actual implementations, Mockito ensures efficient and reliable unit testing, supporting thorough validation of business logic. Roboltrick enables Android tests to run directly on the JVM, eliminating the need for emulators or physical devices. It simulates the Android runtime environment, providing access to APIs and supporting UI component testing. Roboltrick speeds up the testing cycle and simplifies test setup. Challenges in unit testing Android apps include dealing with the framework's reliance on context and system services, managing dependencies, and handling asynchronous code. Solutions involve using robust frameworks, mock objects, and strategies for testing concurrency and timing, ensuring reliable and maintainable tests. Dependency injection promotes loose coupling and modularity, making it easier to manage and replace dependencies during testing. By injecting mock or simplified dependencies, developers can thoroughly test class logic without interference from complex external components, improving test reliability. The @mock annotation creates a simulated object that mimics real behavior without executing actual code. The @spy annotation creates a partial mock, allowing real methods to be called while verifying interactions or changing specific behaviors. Use mocks for isolation and spies for monitoring real interactions. Avoid anti-patterns like testing implementation details, overmocking, too many assertions, and ignoring test failures. Focus on validating behavior through public interfaces, use real objects for simple dependencies, limit assertions per test, and maintain test suite integrity for reliable results. Adopt clear naming conventions for test cases, such as method name state under test expected behavior. This format conveys the method being tested, the condition, and the expected outcome, making tests easy to understand and maintain. Consistent naming improves test clarity and collaboration. The when statement in Mockito defines mock behavior for specific method calls, controlling return values or actions. The verify statement checks whether a method was called on a mock during the test, ensuring expected interactions. These tools support precise and reliable unit testing. Argument capture in Mockito captures arguments passed to mock methods during tests. This allows verification of method calls with specific parameters and manipulation of arguments for further assertions. Argument capture enhances test flexibility and supports thorough validation of interactions.